Let's do some calculus. So calculus is all about the infinitesimal summing of things, or I guess there's a lot of ways you could refer to calculus, but here I feel like is a very good example of what makes calculus different and how intuitive it is. So we're gonna deal with volumes, but now we're getting into the 3D shapes. Now, of course, you can save that for calculus 3, which also covers this, but this is quite intuitive and it takes some understanding. Apparently, it is hard to understand, but for me, it was pretty intuitive and easy to grasp. So we'll move on to the next slide. So much like adding up infinitesimally small rectangles, we do this by adding up infinitesimally small rectangles. So let me go to Sketchpad. So before we wanted to know the area of, let's say, like a velocity curve, and what we would do is we would take the area of each individual rectangle, which is very intuitive. Now we are going to do the same thing. Let's say you have like a water bottle, and of course the water bottle is not uniform. It's a little bit like shaped in very weird ways. You're just going to get the cylinder of each one. Actually, I'm a very bad drawer, but you'll get the cylinder of each one and sum up the volumes this way. So much like you were summing up area with a formula for rectangles, we're summing up a thing using infinitesimally small cylinders. We're summing up a 3D object using infinitesimally small cylinders as opposed to rectangles, which we did with Riemann sums. Now, I'm not too sure why. I mean, there's not a name like Riemann sums here. Maybe someone didn't coin the name. And you can do this for anything because as the slices go to 0, I guess you can write this as the actual volume minus the limit, or no, the limit. Oh, hold on. I guess you could say that for any delta greater than 0 or epsilon greater than 0, you can write a function such as the limit as the integral of an area go minus the area that you have is less than delta, such as the difference between the amount of of b minus a over n is approaching, or as b minus a over n is greater than delta, and you can relate the two with delta and epsilon. But I guess that is a different topic for a analysis class, which is very, very far advanced in math, or further on in math than calculus 1 is. So we can use obviously whatever cylinders, right? And we'll move on. So what is a of x? So now we know that the cylinder formula, and actually, like, I love how we use cylinders and rectangles because those are the foundational definitions of volume and an area. So it's a of x times height. Now this is pretty obvious. Like, let's say you just have a cylinder, the area times the height will give you the cylinder, of course, in a cubed form, right? And you see this in every form. Like, for example, the cylinder formula, assuming that the cross-sectional area is a pi r squared. Actually, I think cylinder is defined as a shape that has a cylindrical base. It's going to be pi r squared times h. Pi r squared is the area, and h is the height. And you can see this with other things as well. Not just technically cylinders. You can see this with like prisms, right? A right rectangular prism would be r squared times h, where r squared is like the base that will give you the height. And you can probably solve this using calculus, but I also think this was simply defined, much like a cylinder is defined. But a cylinder is definitely a little bit more intuitive and I guess can be used better than a prism can for other reasons as well. So let's look at the logic behind it. So like a regular function, let's say that we have a function f of x. This kind of goes back to the calculus idea. And let's say we find the slope. The slope here is pretty small, so like it would probably be around here. So if this is f prime of x, then it probably looks something like this. The slope kind of rises a little bit, then it kind of like goes flatline, so it goes all the way down to 0 and whatnot. So calculating the infinitesimal changes and calculating the area will give you this, because the rate of change for how long it has been changing for will give you the change in whatever that is. That's just what calculus is. And in the same way, let's say we have a function and we have an area function. The integral of the area is actually the volume. And now that might be a little bit difficult to understand, but this is the logic why. And you have to bear with me again. So again, remember that we have area here, and here area will be a function of usually radius. So like a of x or a of r, I guess, would be pi r squared, which means that the area is dependent on pi r squared. And here we have the radius r, and we can see that r is fluctuating here or whatnot. Like this can be 0 and this can be 10 meters or whatnot. But summing up the individual, so if the area here is this, and the distance from that radius is that, then we can calculate that from each very small change, we already know what the area is due to the radius, or how far we are from the original starting point. So like, let's say we have a sphere here, which is probably going to make the most sense. It's a little bit difficult to grasp. We have a sphere here, and let's say that this is r. It will give you the area here, which will probably be a big circle. But hold on, it's a little bit difficult to draw a sphere. I'm going to draw it this way, and this is going to be the center point. And let's say we're going to start at the bottom, which is technically what r is here. R is going to be the distance from there. So at the very bottom of the sphere, r is actually technically 0. And the reason is pretty obvious. It cannot go from side to side because it has no side. So at the very bottom, r is equal to 0. So, and as we go up, the sides become bigger and bigger. So like, let's say we are looking at it's a little bit difficult to draw, of course, but as we are going up, r is increasing to r like equals 2, and that will be the cross-sectional area. But as we're changing from r equals 2, we are also changing from that, because the sphere is technically defined as what that change upwards will be the same as a change to the side, which is how we get that spherical thing. So it's a little bit difficult to grasp, but essentially, as we are moving up through the distance, moving up through the position, the area is changing, and the height is also changing with the area. And as a result, we can multiply the height and the area to get individual small cylinders and sum those areas up, which is the logic behind it. The book doesn't really explain it that well, I don't think, but that is the logic as to why the integral of area is volume. And technically, the derivative of area is circumference, which you can see with the pi r squared formula. You do that. Or you differentiate the pi r squared formula and you get 2 pi r, which is the circumference, which is pretty intuitive. And then you integrate pi r squared, which gives you pi r cubed over 3, or 4 pi r cubed. Wait, hold on. Pi r squared over 3. Integrate that, pi r cubed over 3. Yeah, so integrating that will give you the surface area, actually, which is something else. Actually, hold on one second. Yeah, so integrating that and then multiplying it by 4, because you have to multiply the area because we're integrating from r to 0, which makes sense. Yeah, so the integral of area is also a volume, with a little bit of nuance, of course, because you have to multiply it by 4 because you are simply integrating from r to 0. And r to 0 only includes 1/4 of the rectangle, or the circle, of course. So that's the disk method. And the disk method is used when we can... we have no hole, so that would be like a sphere, as we mentioned before. A sphere is a little bit difficult to draw, of course. This is a sphere. I guess it would work for like a squiggly shape like this, where there is no hole, but it is technically a circle because we can still sum up the individual volumes. But it will not work if you have like a donut shape, and the reason is pretty intuitive. The inside with the hole does not contribute to the area, and therefore does not contribute to the volume. So the logic here is we'll come to what is called the washer method. So there's a disk and washer method, which is pretty funny. I think they're playing on words. I mean, that happens a lot. Like in physics, it's jerk, snap, crackle, pop. But here this is disk and washer method. Disk and washer method. So washer is if there's a hole, so like a donut. And the reason is quite simple. We are using the area base as pi r squared, though technically we don't have to. But for these two general shapes, we are using a of x equals pi r squared. And so the pi r squared of this total area is just pi times big R, assuming that this entire radius is R. And if that small hole is R, then it will be pi r squared minus pi r squared, which is the area. And they simply simplify it by factoring out the r, which is very, very logical, which is very, very intuitive. So now a of x becomes the function pi r squared over r. Now, I don't think I made this clear before, but the integral of the area of x with respect to dx, I guess the variable doesn't matter here, will always give you the volume. So that's why you can do it with things like cones as well, or not cones, because cones are circular too. You can do this with things like pyramids too. But here we are simply just going to use circle formulas to make life a lot easier, and we won't have to explain the other logic. So now we'll talk about rotating y equals square root x around an axis. So there's actually something called Gabriel's horn, which we'll get to a little bit later. I think I mentioned that back like 8 months ago when I was learning calculus. Well, just for fun, just on my free time. Gabriel's horn is essentially where the surface area is infinite, but the volume is finite, which kind of breaks all logic and understanding. But here we kind of get into a situation because what is it? Y equals square root x is very similar, except it actually does converge. Actually, I don't know if y equals square root x comes to a specific value. But like here, it is very similar because now we can approximate a volume. Actually, yeah, approximation, but pretty precise because we are using integrals instead of, well, Riemann sums are integrals as long as n approaches infinity. But here we are assuming n is approaching infinity because we're using standard integrals. So let's take this shape. And again, we are defining this curve. So it wants to know the volume around this curve. So like, it wants to know the volume from here to here if we have to draw the shape out. Of course, the curve is only from the top and bottom. So is it asking? Yeah, so it's only going to ask for, well, hold on. Yeah, but is it asking for, okay, so let's say, oh, rotate, yeah. So rotate is going to mean that it's going to be this entire rotation. So if we had to draw the shape out, like in a visual setting, it will look something like this. So remember that the formula to get volume is just simply the integral of the area function. So first we have to define the area function. Well, in this case, again, we are using circles. This would be the disk method, not the washer method. But the disk method, what is it? It's pretty simple and straightforward. It's just a circle. So we are given that the height of any function, well, let's use some logic here, and let's draw the shape out right here. The height here, which is like, well, if we rotate it, we just simply rotate it. So the height here would just be, well, I guess it would be half because we're only dealing with half. This is the square root function. The height will be the radius at any point. So we can actually say radius equals square root x. But what do we know about the cross-sectional area? It's going to be a circle here because we are using the Disher method, or the method. So simply plug square root x into there to get pi x, and this should be very easy integration. And it says from 1 to 0. So we can integrate this and get pi x squared over 2 is equal to, oh, I already integrated it, so we have to plug in the up and lower bounds. 0 doesn't matter, so it's going to be pi over 2, because 1 squared is just equal to 1. So actually the volume here is pi over 2, and I guess that would depend on what units you are using, but I mean, like, how can we use, like, think about the logic about this. We are using simple calculus to derive like pretty crazy 3D shapes and stuff, and it might not seem that crazy, but like math is, or like, it is really hard to find order in like the natural world of things, and math can simply find you the precise area and volume every single time. So, well, not every single time, but most times, and that is how you do the thing. So remember that volume is simply the integral of area, and the reason it works is because area times the position, or the change in position, will always just give you that. At least for circles, and for cylinders, we're simply summing up the infinitesimally small change in position between the radii, which is the same exactly. Radii, because we're using obviously the disk method, so that is calculus. So yeah.